This is Step 1, 2011, Question 9. We're told that a projectile is projected from the horizontal at an angle θ to the horizontal and passes over two walls, one of height d2 at a distance d1 from the point of projection, and one of height d1 at a distance d2 from the point of projection. We're also told that the particle just passes over the walls, i.e. it passes through the tops of the walls A and B, which I've labelled here, and I've called the point of projection O. So we're asked to show that tan theta equals d1 squared plus d1 d2 plus d2 squared over d1 d2. So what we want to do here with this question is, looking at this equation here, we're trying to relate tan theta to the vertical and horizontal displacements. So how are we going to do that? Have a think yourself about a good formula to use to relate tan theta to vertical and horizontal displacements in projectile motion. A good hint would be that we should be using Cartesian coordinates, so taking the upward direction as y and the horizontal right direction as x. So the best thing to use is Cartesian equation for projectile motion. You would have hopefully derived this yourself, but I'll have a run through the proof of the Cartesian equation for projectile motion. So the way we do this is to try and relate the y and x coordinates of the projectile, and we're going to get a quadratic n tan theta. So the equation that we use, the Suvat equation we use, is s equals ut plus half at squared. So we need to consider vertical and horizontal motion separately. So vertical motion, we get y equals ut sine theta minus half gt squared, where g is the acceleration, minus g is the acceleration of the particle moving upwards, and u sine theta is the vertical component of velocity at O. And then looking at horizontal motion, we know the acceleration in the horizontal direction is 0. So, and the horizontal component of velocity at O is u cos theta. So we get x equals ut cos theta. And we can sub equation 2 into equation 1 to try and eliminate t. So you can have a go at this yourself and pause the video, and then I'll show you what the equation comes out as. So finally, relating y and x, by subbing 2 into 1, we get y equals x tan theta minus half g x squared over u squared times 1 plus tan squared theta. So what do we know about the projectile, and how can we relate it to the Cartesian equation of motion? So we know that the particle moves through the points A and the point B. And point A can be written in Cartesian coordinates as d1, d2, and the point B can be written in Cartesian coordinates as d2, d1. So, since the particle passes through these points, we can sub them into this equation to get two equations. So we get this and this, just subbing in d1, d2 in the appropriate places for y and x. So here are the two equations we have. And what we want is to get this, tan theta. But we have a tan squared theta in here, and that's something that we want to probably get rid of. So we can get everything in just tan theta, because we don't want to be dealing with a quadratic. So what do you think would be the best way to get rid of this tan squared theta, or even in fact the 1 plus tan squared theta, which is common in both? So we can actually eliminate this by expressing 1 plus tan squared theta in terms of the other terms and then subbing it back into the equation. So from equation 4, since we want to eliminate 1 plus tan squared theta, we write 1 plus tan squared theta as 2 d squared tan theta minus d1 times u squared over g d2 squared. And we can sub this back into equation 3. So when we sub it back in, we get rid of the tan squared theta completely. So we get d1 tan theta minus half g d1 squared over u squared times 2u squared times d2 tan theta minus d1 over g d2 squared equals d2, as equation 3 says. And then simplifying this and cancelling terms that are the same, we cancel the g's, the u squares, and the 2's, and that's starting to look a little bit more like this because we didn't have any of the other terms in here. So what are we dealing with now? We've got d1 tan theta minus d1 squared over d2 squared times d2 tan theta minus d1 equals d2. So remember that we want to isolate the tan theta because we want to find tan theta in terms of d1 and d2. So let's have a go at getting the tan theta out. So we get tan theta times d1 minus d1 squared over d2 plus d1 cubed over d2 squared equals d2. And then we can put this under a common denominator, so we get tan theta times d1 d2 minus d1 squared over d2 plus d1 cubed over d2 squared equals d2. Then subtracting this term from both sides and putting it under a common denominator, we get this. And on the right-hand side, we get d2 cubed minus d1 cubed over d2 squared. Now, if you know a very handy tip on how to simplify this or factorize it, have a go at doing that yourself. So actually, things like this, so d2 cubed minus d1 cubed, actually has a very handy factorization that you should try and put to memory. Or d to the n minus d to the n. So any term, this can be an n anywhere. So remember this tip, it comes out as d2 minus d1 times d2 squared plus d1 d2 plus d1 squared. And if you multiply these two brackets, you should be getting this. And so we've got, factorizing this left-hand side as well, we've got a d2 minus d1 on both sides, which we can cancel. And then finally, cancelling the d2s at the bottom, one of the d2s here, and then dividing through by d1, we'll get tan theta equals d2 squared plus d1 d2 plus d1 squared over d1 d2, which is exactly what we wanted at the start of the question. For the next part of the question, we're asked to find and simplify an expression in terms of d1 and d2 only for the range of the particle. So to find the range of the particle, we can do it by many ways, but once we've already obtained the Cartesian equation of projectile motion, it's best to use that. So here's our equation from before that we derived, and we need to find the value of x for which y is 0. So there are two values because this is a quadratic, either y is 0, which is just a start, or x is 0, which is just a start, or x is the whole range. So we want to find x when y is 0, and we'll call that r, we'll call the range r. And so we need to solve the equation r tan theta minus half g r squared over u squared 1 plus tan squared theta equals 0. And so first of all, we know that we've got a quadratic in r. So just writing it more explicitly as that quadratic and multiplying through by 2u squared g, we get this quadratic. And note that r can't be 0 because that's just the starting position of the particle, so we can just divide through by r. So we've got r 1 plus tan squared theta equals 2u squared over g tan theta. And now we know what tan theta is in terms of d1, d2 before, but first of all, let's deal with this side, the 1 plus tan squared theta. And can you think of a way to simplify this expression to try and get rid of the more complicated terms? Something that we've done before. Okay, so from before, we worked out that 1 plus tan squared theta is indeed this expression in d1, d2, u squared, g, and tan theta. So if we sub this in, and this is quite neat, when we sub this in, we can see that we've got u squareds, g's on both sides, and the 2, so this just cancels. So just moving on to another page here, we have cancelled the 2 u squared over g's, and that gives us r over d2 squared times d2 tan theta minus d1 equals tan theta. And now we have an expression in terms of d1, d2 tan theta, but our aim is to find an expression in terms of just d1, d2. Well, in the previous part, we had an expression for tan theta in terms of just d1, d2. So let's sub this in both the places that tan theta is in this equation. So subbing it, first of all, rearranging this to d2 squared tan theta over d2 tan theta minus 1, and then subbing it in. So this looks quite a big expression, but actually we can cancel the d2's here on the denominator, and we've got this expression here. And what we should do now is, noticing that we have a d1 on the bottom in both cases, multiply the top and bottom by d1. So doing that, we note that this goes to d1 squared plus d1 d2 plus d2 squared minus d1 squared, so the d1 squared cancel, and we just get this numerator on top. So multiplying d1 top and bottom, we get d2 times d1 squared plus d1 d2 plus d2 squared over d1 d2 plus d2 squared. And if you notice, the top and bottom both have a d2, and so we can cancel this, giving us d1 squared plus d1 d2 plus d2 squared over d1 plus d2 for the range of the particle in terms of just d1 and d2. And then that's the end of the question.